Welcome, my name is Marco Coisson and I am a researcher at the Italian National Meteorological Institute. One of the core components of a vibrating sample magnetometer is the electromagnet. It consists of an iron yoke, this one, and of copper windings that are used to let a current flow and generate the magnetic field. The current windings are powered by a power supply that is capable of generating approximately 150 ampere to power this magnet. And once the iron yoke is magnetized, the actual magnetic field is generated in the gap between the two conical shape expansions. The two expansions are made of a magnetic material that is very soft and that has a high saturation, in order to ensure that the field is as strong as possible in the gap, but also with a shape that ensures a certain volume of homogeneity of the field. In this configuration, the magnet is capable of generating up to 1.7 Tesla of magnetic field, but if the gap is reduced, we can slightly overcome the 2 Tesla threshold for the magnetic field. Conversely, in this configuration, the volume of homogeneity of the magnetic field in the middle of the gap is of approximately 20 cubic millimeters. In order to control the magnetic field, the applied magnetic field, the system is equipped with a software that performs a feedback. So the power supply is driven by the software with a certain current value, but in order to know which magnetic field corresponds to that current value, there's a whole probe placed in the gap of the magnet, in the middle of the gap of the magnet, that reports the applied field value. A closed feedback allows the software to control the magnetic field, setting it to the desired point value. Since the power supplies are bipolar, the magnetic field can be controlled continuously from positive to negative values and back. The second core component of a vibrating sample magnetometer is the vibrating head, which is a linear motor that is encapsulated in this box here. The role of the box is to keep the temperature constant of all the vibrating material, because as we have seen in the theoretical lesson, it is extremely important that the system is capable of keeping the vibration amplitude and frequency constant during the measurement. The head is this linear motor to which the rod is attached that goes to the gap of the magnet, and there the sample will be installed. But for precise positioning of the sample into the magnet gap, there are also positioning screws, micrometric positioning screws, that allow the movement of the head and of the attached rod and sample along the Y direction, along the X direction, and along the vertical direction, the Z1. Certain heads have also the possibility, through a knob and maybe a motorized mechanism, to rotate the sample with respect to the direction of the applied field. The last core component of a VSM are the pickup coils, which are these plastic items here, which are glued to the surface of the polar expansions of the magnet. A detail of the coil is available here. You can see the two windings that are placed one on top of the other in the actual mounting. The coils are placed in this way. This is the bottom of the magnet, the top one, and the sample vibrates vertically along this direction. There are two sets of coils, one on one side, the other on the other side. And as you can see here in the back, there are electrical connections that allow to connect them from the left side to the right side in the proper way to ensure that the region of uniformity and maximum sensitivity is in the middle of the gap, as we discussed during the theoretical lesson. The typical way to install a sample into a VSM is to use specific sample holders. Here we have two examples. One where the sample can be mounted in this way, and so the field will be in the sample plane and the sample will be able to rotate in order to keep the field all the time in plane. The other configuration is this one, and so the field will be applied in this way, or upon rotation the field will be able to explore all the angles from in plane to out of plane and all the intermediate positions. The sample holders might be, but maybe even others that one can prepare directly, then are screwed at the end of the rod that is attached to the vibrating head. How do we keep the samples in place on the sample holders? Normally there are two different methods. One is to use a vacuum grease that offers enough viscosity to keep the sample there, but of course it is a dirty process, so if the sample needs to stay clean, it can be difficult to clean afterwards. The other possibility is to use Teflon tape, PTFE tape, that can be used to envelope the sample and keep it in position. Here we have a selection of possible samples that can be measured with a vibrating sample magnetometer. The classical objects that one would like to measure are bulk samples like this one. Anyway, it is not a conventional bulk sample, as it is a nanocomposite. It is a polymer which embeds nanoparticles. Another example of bulk sample is this one, which is an Alnico hard magnetic alloy in a form of a disc, of a cylinder, that can be placed on some of the sample holders that we discussed before. Another typical example is a thin film, so a substrate with a magnetic coating of some kind. In this case, the thin film is even patterned, so there are microstructures designed on top of it. Another example is made of nanoparticles. This sample holder is similar to one of those that we have seen before, but this is empty, and inside you can put a known quantity amount of nanoparticles in order to measure their magnetization. Another example is this ribbon here. This is an amorphous ribbon. Of course, it is very, very long. You must cut a small piece of it and put it on a sample holder in order to measure its magnetic properties. Especially when high sensitivity is required, the way you mount a sample is extremely critical. This is the way you mount a sample on a typical vibrating sample magnetometer. This is the sample holder that we examined before, and your sample, the thin film in this case, is placed here at the end of the sample holder with a small drop of silicone grease, of vacuum grease. But as we discussed in the theoretical part, the problem is that every interface, every discontinuity in the materials that go inside the gap of the magnet brings a magnetic signal that affects the measurement. That's the reason why when you use a squid magnetometer, you want that the rod continues after the sample in a way that is as homogeneous as possible. That's the reason why not only the quartz part of the rod goes beyond the sample that is in the middle, but also the Teflon tape that you use to put the sample in place is wound around the quartz part very far from the sample, and will keep on being wound around the quartz part just to the bottom, in order to ensure the maximum uniformity of the rod and the Teflon tape, so that there are as few discontinuities in the material as possible, and all the discontinuities can be attributed only to the sample that you want to measure. Now it's time to calibrate the vibrating sample magnetometer. We use the nickel sphere, which is here, that is provided by the manufacturer. It is placed into a sample holder similar to the others that can be screwed at the end of the rod that will be inserted in the magnetometer. Now that the nickel sphere is installed, we apply a magnetic field that is capable of sustaining the magnetization of the nickel sphere to saturation, and then we must center the sample in the gap of the magnet. The first operation is to move the sample along the Z direction, and then we move it along Y and X. Here you can see the positive peak during the centering along the Z direction, followed by the negative one when the sample is so off-center that is close to one of the two pickup coils. If you recall them, they were one up and one down. When the sample is here, in the middle, you have the positive peak. When it is close to either the up or down coil, you have the negative peak. This is the correct center position. We must repeat this operation for Z and Y, and we must find a minimum, as we discussed in the theoretical part, for the X position. Once the coarse centering is done, for the fine centering, I repeat the procedure along the Y, X, and Z positions in order to find the correct placement of the sample in the gap. The calibration is done by comparing the reading of the pickup coils with the known magnetic moment of the nickel sphere at the known applied magnetic field. Now we have replaced the nickel sphere with our unknown sample. In order to do this operation, we must switch off the vibration and then switch it on again. Before doing the measurement, it is extremely important to verify that the vibration has reached a constant amplitude, otherwise the signal will drift. In the graph you can see that in the first few seconds or tenths of seconds after switching on the vibration, the signal drifts until it reaches a stable state. In order to do our measurement, we can choose between a measurement of magnetic moment as a function of field, time, temperature, or the angle between the sample and the applied magnetic field. For example, we want to proceed with a measurement of magnetic moment as a function of field, and there are different options for what concerns the field history to which we want to submit the sample. The simplest is the hysteresis loop, from positive saturation to negative saturation and back to positive saturation. We can define the vertex field, the field increment, and this automatically calculates the number of points that constitute the hysteresis loop. As you can see, the value is updated in real time. The signal that comes from the pickup coils is filtered by a lock-in amplifier, which has a time constant that can be selected by the user. Longer time constants are useful when the signal is particularly weak or noisy. Also, you can choose the integration, the averaging time. So for how much time you want to average the signal that comes from the lock-in amplifier in order to get rid of some noise and have a better measurement. Another critical parameter is the acquisition mode that can be continuous or point by point. Point by point means that the VSM brings the field to the desired value. For example, the first field will be at 1 Tesla, stops the field there, then measures the magnetic moment, then applies the increment or decrement. So for example, it will go to 0.9 Tesla because the increment is 100 millitesla, stop the field there, measure the magnetic moment again, and this will go on until the whole loop is completed. The whole loop or the whole field history that has been selected by the user is completed. Continuous instead means that the field will vary from the initial value to the final value with a certain rate, but it will not stop at every field point. Instead, once the field reaches the desired field point, then the magnetic moment will be measured, but in the meantime, the field will keep on moving at the same ramp rate. This means that the measurement will be faster, but also less accurate. And especially for long time constants or long averaging times, the discrepancy between continuous measurement and point by point can be significant. For the moment, we do a measurement in the point-by-point configuration. We are now measuring the hysteresis loop. The magnetic moment as a function of the magnetic field is measured at several different points, the ones that we have selected when preparing our experiment, one by one, because we selected the point-by-point procedure. As you can see, a point at a time, the hysteresis loop is constructed. Now we have completed the two hysteresis loops. Here in the same graph, we plot the hysteresis loop of the sample measured in the continuous configuration, the black symbols, squares, and in the point-by-point configuration, that is the red circles. Overall, it seems that the two measurements are more or less identical, even though the continuous measurement took a fraction of the time of the point-by-point measurement. But if you magnify close to the remanence or the coercivity, you can see that there is a discrepancy between the two techniques. So depending on what you want to obtain, if you are doing a quick screening of the material's properties, the continuous configuration is certainly faster, but if you want to assess the magnetic properties of the sample in a more accurate way, the point-by-point configuration is by far the better.